Today we have 5 computer power supplies on the table. They came in together and they are all broken. We are going to try to diagnose and repair them. I have never checked which one has what kind of a problem yet. We are also going to do it together. Let's first identify the problems, like 5-volt standby, 12 volts, 5 volts, 3.3 volts, or total short, a catastrophic short, and note them down on each unit, on each PSU, power supply unit. Let's turn the overhead lamp on and see. Let's start with the first one. I have a power cable here. What model are them? They are from Aerocool. I don't know how to pronounce this word. Cylon? Cylon? I don't know. 500 watt, 80 plus bronze units. Let's see. Let's plug the power cable in. It's on. Let's see. I have a light bulb in series with the wall. Okay. The bulb just flashed for a second. This is normal. So let's see. I'm going to plug the negative probe on one of the middle pins in a Molex connector to probe the ground. Let's get our multimeter here in voltage mode. And let's give it some power. Now it's directly connected to the mains. Let's see, we should have some voltage here and here. This is the PS on, normally the green cable. And this is the 5-volt standby. Both are present. Let's see what happens if I short the PS on to one of the ground pins. I'm going to probe 12 volts while doing that. 12 volts should be on the +4. Let me check where I can find them. Normally these cables are colored. Let's see, on the +4, this one should be 12 volts. Let's probe it. This should be the PS1. Let's check it again. Yeah, 3.8 volts is normal for PS1. Let's try to turn it on and see what happens. Do we have 12 volts? Yeah, we do. Let's check the other voltages. 5, okay. 3.3, okay. So this doesn't look problematic actually, but we should test it with some load. So I'm going to write one for the first, and looks okay. Check on load. Okay, let's unplug it and put it aside for now. We have the second one here. Let's plug our power cable. Check the light bulb. It just flashed for a second, which is normal. I'm going to do the same thing. I'm going to probe ground from I experienced some problems with my overhead lamp. Now we are fine. Let's continue with the second one. I'm going to probe ground the same way. The middle two pins are ground on a Molex connector. Let's probe the ground here. The light bulb flashed for a second. That's normal. Let's connect it to the wall directly and check. This is the 24 pin. We should have, let's see, 5-volt standby here, which we have, and PS on here. We also have that. This is 12 volts. And let's short the PS on with the ground to see. Okay. It started. And immediately the voltage dropped. It shut itself down. So we have a problem with this one. Let's see. I'm going to write 2 per second. 5-volt standby and PS on. Okay. Shuts itself down. Let's also put this one aside now. Let's unplug it. And now we have the third one. Let's also plug that in. And now I'm checking it with the bulb. It just flashed for a second, which is normal behavior. It happens because the capacitors on the high voltage side, the bulk capacitor, is getting charged. While getting charged, it lets the current pass and light bulb flashes. When it's charged, it doesn't let the current pass. It acts like a resistor, like open circuit actually, and the light bulb shuts down. Let's see. Let's connect it to the mains. Okay, do we have 5-volt standby? Yes, we do. Do we have PS on? Yes, we do. Let's connect it to 12 volts and shut PS on. Okay, we have 12 volts. We have 3.3. We have 5. Okay. This one actually looks alright. Fan is spinning. So let's shut it down. Three. Looks okay. Check on load. We have two left. Cables. Okay. I separated them. Let's check this one. This one looks opened before. We have a dent here. Let's plug the power cable in. It's on. Let's check with the light bulb. It doesn't turn on. Seems like we have a blown fuse. Before open circuit. Probably a blown fuse. We have the last one here. Let's see. Power cable. It's on. Let's check with the light bulb. It doesn't flash. Do I have a problem with my light bulb? Let's see. I have the first one back. I'm going to try it. Okay, it flashes. So this one is also open circuit. Probably a blown fuse. Five. Let's say open circuit. I was going to write blown fuse, but it's a open circuit. Okay, which one should I be checking? I can check 1 and 3 out of camera. They are going to be tested under load. We have 2, 4, and 5. Okay, we have 5 in front of us. So let's start with 5. Let's check the specifications first. We can get 37 amps from 12 volts, which is equal to 444 watts, which is all right. I can say all right for a 500 watt power supply. It says 80 plus white, not bronze, silver, gold, or anything. This one might be a little older. Let's see. Let's open it. Actually, while opening it, I have to warn you that a power supply can hold charge inside the bulk capacitor. I'm going to show you what it is. Is this one opened before? Yeah, this one was opened before. This one is the bulk capacitor and it holds charge when you plug it to the wall. Even if you disconnect it, it still holds charge and it's over 300 volts voltage on this capacitor. It's rated 450 volts, I believe, yeah. 220 microfarads, 400 volts. If it's 400 volts, I believe this one doesn't have an active PFC, a power factor correction circuit. It's pretty normal these days. Does it say anything? Active or passive PFC? No, it doesn't. Can we get the fan out? Looks like it. We are going to need this one later. Let's get the cables out. Okay. We have 4 screws. Let's also unscrew them. Before the last 2 screws, I can see the fuse right here. This last thing is the fuse. Let's check it. It should be reading short circuit. Yeah. It's open circuit. So the fuse is blown, like we thought. I'm using a bulb in series to limit the current if we have a dead short. If we have a dead short and we connect it directly to the wall, we are going to trip the breakers, or worse, it's going to explode if the breakers doesn't trip. Okay, we have a plastic cover here glued to the board. Okay, the bulk capacitor is here. I don't believe it has charge now because the fuse is blown, but I'm going to check it anyways. Better safe than sorry. These are the legs for the bulk capacitor, and we don't have any charge. Okay, it's safe to touch then. Let's also desolder these two wires to be able to work on the board more comfortably. I don't want to do something like this all the time. I want to see something. I'm going to get some solder on the tip to be able to transfer heat easier. It's still heating up. Yeah. Let's get this one out and also this one. Okay, cables are out. Let's put this one aside for now. Okay, let's start from the wall. The wall is connected here, the mains voltage. It passes through this fuse right here. Some passive components, some capacitors and inductors. And it comes to the full bridge rectifier here. It consists of 4 diodes to rectify the AC voltage. We're in diode mode. Let's check whether we have a short here. Yes, we do. From the mains. Looks alright. Okay. We can't say the full bridge rectifier is shorted because we have a diode value here and here. AC is connected to the middle 2 pins and we have 2 diodes connected from them to here, and this pin becomes the rectified positive, and we have 2 diodes from the rectified ground to these pins to AC, and we can see that they look healthy, these diodes. We can see 4 diode values. That's why I don't believe the full bridge rectifier is the culprit here. But we have some short between the rectified positive and the ground. Let's continue. After that, we have another inductor and the bulk capacitor. We are going to see a short on the bulk capacitor also. No, we don't. What? Actually, what? The rectified voltage should come here directly, but looks like it goes through a diode here. Yeah. This one connects the ground to the negative side of the capacitor. That's why we don't see anything this way, but we see a diode value this way. The same value here and here. Okay, then we should check this one, and we have a short. But after this diode, we don't have a short. So I'm thinking again, and the full bridge rectifier might be broken. Because we don't see a short after this diode. Yeah. Let's desolder the full bridge rectifier here. And if it's the full bridge rectifier, this is going to be a pretty simple repair. Let's see. I'm going to apply some leather solder to decrease the melting temperature of the factory solder. Let's get some solder wick here. I'm going to get a different one because it was too thin. Okay, let's check the pins. We might some more wick. Yeah, they're all moving, so I believe we have some glue here. Let's get rid of it. Now we should be able to get the rectifier, full bridge rectifier off the board. Yeah, we have it right here. Let's put the board aside for now and check the bridge rectifier out of the circuit. We should have some markings here. Yeah. The middle two pins are the AC, and the pin here is the rectified positive and rectified negative right here. We should have two diodes from AC to rectified positive. Yeah, we see the voltage drop. And we should have two diodes from negative to the AC, from rectified negative to the AC side. And yeah, this looks alright. But voltage drop here should be the double of these two, actually. Around 1160. Let's check the circuit again. Yeah, we still have a short, but not here. The ground is connected through a diode, and the switches here, MOSFETs or the transistors here, use the voltage from the capacitor, and we don't have a short here. That's why I believe we have the short before the diode. So I'm going to check capacitor right here. It should be a capacitor. And what is this? Is this a thermistor or... Yeah, this should be a thermistor. Its resistance should depend on the temperature. Yeah, when it's cold, it should have a high resistance, and when it's hot, it should have a lower resistance. This is here to limit the current, or while charging, these capacitors can actually trip the breakers if this wasn't there. This is here to limit the inrush current, and after it's hot, its resistance is going to be very negligible. Okay, let's also get the capacitor out then. I don't know what to do actually. This diode isn't here most of the time. That's why I'm a little bit confused. And most of the time, bridge rectifier goes bad when something else is short, like the transistors, the MOSFETs. But they don't look shorted. I haven't checked actually, but I don't think they are, because the capacitor looks alright. The bulk capacitor, I mean, not the one I am desoldering right now. These don't go bad most of the time, but let's check it anyways. Diode mode, let's see. Yeah. We don't have a short as we can see, but we still have a short right here. No, we don't. What happened here? This one doesn't look to be shorted, but was it shorting something else? Why don't we have a short right now? Yeah, we don't have a short anymore. It looks like what? I removed this capacitor and the short is gone. But this capacitor is not shorted. What? I don't understand. Let me get some alligator clips because I believe I can't probe this capacitor like I should. Or what happened here? I have absolutely no idea. Yeah, absolutely no idea. Yeah, this looks like a current sensor resistor. A very low value. Yeah, we still have a short. See? Yeah, okay. My probes weren't touching. Oh, we also desoldered the current sensor resistor. That's why. That's why. Yeah. We still have a short. Yeah. Okay. Let's solder the current sensor resistor back. Yeah. That's why we couldn't see the short. Now we can see here. Okay. Let's continue then. Let's check the transistors. I believe these are MOSFETs because the transistors should normally has the transistors normally have a diode near them because when the magnetic field in a coil or a transformer collapses, it creates a reverse voltage, very high reverse voltage. That's why there's a diode there normally, a reverse in reverse. We don't see them there because MOSFETs have them internally. That's why I believe these are MOSFETs. Let's check them. This one looks alright. Where are the pins for the other ones? Let's check this one. This one looks to be shorted, but we have to check it out of the circuit because something else in the circuit might also be short. Let's check here. Yeah, we can see it here. Let's get this heatsink and all the components on the heatsink out and check them out of the circuit. Okay, we have them out. Let's check the model numbers. ITA 13 and 50R. And this should be a diode. PFC D86G. Yeah, this is a diode, and these are, according to the name, 13 and 500 volt N-channel MOSFETs. Let's check them. We are in diode mode. Yeah, we should see a diode here, but not the other way. Yeah, this is the diode I was talking about. Let's see this one. And we have a diode value from here to here. We don't see anything. Yeah. Yeah, okay. It looks fine. This diode is way for 157 millivolt voltage drop. This way, we don't see anything. Let's check this one. Yeah, this one is gone. Definitely gone. Okay. We have a problem with the MOSFET in D. And we can see, after seeing this, we are sure that this one has active PFC, active power factor correction. And this is the transistor for the active PFC. Active PFC is actually a boost converter. It boosts the voltage up. Power factor correction is something, a big topic actually. I can't tell what it is in a video like this. You can research it, but it's actually a boost converter. It's enough to understand what's going on here. I'm going to check the datasheet, and there is some thermal paste at the back side. Okay, ITA 13 and 50R. Let's check the datasheet for this, and let's check I have something similar or the same in my stash. Here is the datasheet for the ITA 13 and 50R. This is the MOSFET we had on the board, the broken one. As you can see, it's a 500 volt 13 amp N-channel MOSFET. And I have another one here. This one I could find in my stash. This one is actually a little bit stronger. It can continuously pass 18 amps, and it has a maximum of 500 volts as our original MOSFET, but this one can actually allow more current from drain to source. And as we can see in the symbol, we have a diode from source to drain, and we could see that diode while measuring from pin 3 to pin 2, but we couldn't see any voltage drop or diode value from pin 2 to pin 3 because the diode is from the source here to drain. If a power supply uses power transistors instead of MOSFETs, MOSFET stands for metal oxide semiconductor field effect transistor. But if it was a BJT, bipolar junction transistor, a silicon one for example, a silicon power transistor, we would see a diode actually on the board, a separate diode, but we don't see it with MOSFETs because MOSFETs have this diode internally. As I said, we had this one, but I'm going to use this one instead. And let's continue. Here we have some new parts. Totally brand new. You should have no doubt that these are brand new. Okay, this is our MOSFET from our power supply. Let me show you the values again. We have 34 millivolt voltage drop. Short. Yeah, this short here proves everything, and this is our replacement one. We see nothing. We see nothing, and we should see a diode value here, and we shouldn't see it the other way. Yeah. Okay, this one is good. Like I said, this is even stronger MOSFET from this one. Let me apply some thermal paste. Okay, let's clean it before we apply some new thermal paste. Okay, looks clean. These are some alcohol wipes. You can use ethanol or isopropyl alcohol as you wish. Let's apply some thermal paste here. This should be enough. And let's also put this thing if we can. On this leg. Let's straighten it. Okay. Now we can put our MOSFET on the heatsink. Let's screw it in. Okay, it's in its place. Now we have another full bridge rectifier here. This says GBU 608. 608 means 600 volts, 8 amps. And we have here KBU 1010. This means 1000 volts and 10 amps. This is the other one. Let me show you the readings. Once again, we should have from AC to rectified plus to two diode values from here, from the AC to the rectified positive and from the rectified negative to the AC. Yeah, we see. And we have something like 800 millivolts here. Okay, let's check this one. On this one, this side is the rectified positive. Am I wrong here? Yes, I am wrong. Rectified positive is the right side. 597 millivolts. Okay, it's close enough. Yeah, actually, it shouldn't be double then. I remember it wrong. Okay, I'm going to put this one anyways. Let's reassemble the board. We didn't check for a short after we got the heatsink out, but let's check anyways. I don't think we have a short now. Let's see. Yes, we don't. The other way. We don't have a short anymore, as we can see. Yeah. Then we can say that the cause of this short was this MOSFET on the active PFC part of our circuit. Let's reassemble our board and test it. Okay, I reassembled the board with the new MOSFET. I couldn't fit the new full bridge rectifier here because there isn't enough clearance if I put this capacitor back. That's why I used the original one. And moment please. I need to secure my overhead lamp after this video. Seriously. And I soldered the fuse here because I don't want to bridge it, but I don't want to change it yet. That's why I have this fuse for this kind of purposes. Okay, now we can try our power supply. I'm going to solder the wire back to their places. So how was it? Oh, I need to desolder this leg. Okay, I'm going to secure my lamp properly this time and come back. I'm back. We are a low budget channel here. We may have some problems like that. We are no professionals. Okay, am I missing something here? hole is there. There's this second hole. Yeah, here we are. Okay, live here. Let's solder it. Let's get rid of our old MOSFET. Okay, the other cable. Okay, both resoldered and secured. And I'm also going to get the fan for some visualization. We can visually see whether it's on or not. Okay, fan is connected. Yeah, let's get a power cord. Power supply is on. Let's see. The bulb flashed for a second. It wasn't doing that. Now let's check before powering it on. How much, how many volts do we have here on this capacitor? The multimeter is here. I'm going to probe the capacitor here. We have 35 now because it's off. I'm turning it on again. Let me show you the capacitor voltage. It's 317, 18. Even if I turn it off, the voltage is going to stay there for a moment. Actually, since this has active power factor correction, it's going to drop fast, but if the power factor correction circuit is open circuit, then it's going to stay there for a long time. Let me now probe the 5-volt standby and the PSU voltage. I'm going to use the Molex connector for ground, like I did before. And let's check. This should be 5-volt standby. What do we have here? 5-volt standby. Nice. What do we have on PS on? Yeah. Now I'm going to probe 12 volts from here and short the PS on pin. Let's connect it directly to the wall. It was still in series with the light bulb. Let's see. Yeah, we have 12 volts, and as you can see, the fan is spinning. Let's check 5, 3.3. Nice. This looks repaired. Let's Also, let's first turn it off. Let's also replace the fuse and clean the board. After that, I'm going to reassemble it. Let me show you the voltage on the volt capacitor again. Let's see. 26 volts. It's actually safe, but I'm going to show you what to do if you are ever in the situation. I have a 10k power resistor here. This is a 10k power resistor, and I soldered some probes to this resistor. You can have a 5k, 2k, 3k, whatever. And instead of shorting these two legs of the capacitor, you can use a resistor instead. But be careful, this is a 10 watt resistor. This is actually more than you need. But still, don't short them. Let's check the voltage again. I'm going to use a lower range. Okay. Yeah, half a volt. This is totally safe now. So let's solder a proper fuse here. It should be something like an 8 amp or at least 6 amp fuse. Let me check actually. This was a 6.3 amp, weird value, but it's a 6.3 amp, so I'm going to use a 6 amp fuse instead and reassemble our unit. We have a system here. This is an X58 motherboard. There is a Xeon X5675 in the socket. We have 12 gigs of RAM and an RX 570 as our graphics card. Let me show you what you can do with the 5V standby. Actually, the power supply is on right now, but the computer is off. I'm going to show you something. We have a phone here. I'm going to plug a charging cable to the USB port of the motherboard, and I'm going to plug it into the phone. And as you can see, it's charging now. So this is coming from the 5V standby. If you have some keyboard with LED or something, it's going to be on even if the motherboard is off. And we have some passive voltages on the motherboard right now. The motherboard knows whether we have a CPU in the socket or not with this passive power, passive voltage rails with the passive voltage rails. So let's turn it on. And I've overclocked the CPU actually. Okay, it's on. I've overclocked the CPU to 4.3 gigahertz on all 6 cores. As you can see here, to get an even higher power consumption. Let's see. Normally, you would use a power supply like this with an i5 or a Ryzen 5 and a graphics card with around 150 watt max power consumption. The CPU uses a little bit higher when overclocked. This one should actually be consuming like 140, 150 watts right now with this kind of overclock. And the graphics card should be around 130 under full load. Let me show you. I'm going to also open CPU Z. I don't know why this happened. It looks alright. It's at 4.3 gigahertz right now. And we have an RX 570 from Sapphire. Okay, let's start a firmware test. I probably have a problem with my HDMI to VGA adapter. Yeah, looks like it. Yeah. Now we have a picture. Okay, the computer is still running. It's an adapter problem. Let's see. The GPU is drawing around 130 watts right now, as we can see. And I'm going to also start Prime 95. Sorry for the screen. I need a new adapter, I think. Yeah. CPU is at around 78, 80, you can say. 80 degrees Celsius. And it's probably drawing like 140, 150 watts. And the GPU is drawing 130 watts. But the GPUs actually spike, and sometimes they draw double the power they're normally using on average. Your power supply should be ready for this, or it's going to shut down to protect the board and itself. To protect the motherboard and itself. I meant motherboard while saying board. Okay, let's... For how long it has been running? 2.5 minutes. Let's test it for at least half an hour and check again. Okay, it's been more than an hour, 66.5 minutes, and the PSU is still running. But I had to return back to the factory clock because I received some blue screens. It's an instability issue when you overclock. That's why I decided to use the CPU in stock settings. It still consumes a lot of power, more than 90 watts. The max TDP is 95 watts. Like, you can think of it like around 100 watts it can consume, and the GPU also consumes around 130 watts, so we can say that it's a moderate load for a PSU, and you should use a PSU like this in a computer like this for a Ryzen 5. Yeah, I need to replace my adapter. Okay, now we can shut it down. And looks like that's it. We have our power supply repaired. It's a little bit warm, but it's not like that hot. I'm happy with it. And one of my friends yesterday told me to go make another video. He wanted to watch something. This one is for you. You know who you are. If you run out of battery, you can use this one now. So it was it. If you have any questions or suggestions, please let me know in the comments. And let me know which one should we repair. I don't see anything to repair with the first one and the third one, but we still have the second and the fourth one here. This is the fourth one, the open circuit one, and this is the second one, which shuts itself down. Let me know in the comments which one you want to see, the second or the fourth one. And we can do a video on the one you choose. Thanks for watching and see you in the next video. Goodbye.